So, all right. At the end of last class, we ended with this so-called bilinear form. And then showed that if B is bilinear and symmetric, I don't know why it does that. It doesn't always open on the first page. So I'm going to try it again. Okay. So if we have a bilinear symmetric form, then we can use that to infer a quadratic functional that looks like this. And if we want to, then now we have a functional, like, you know what I mean? Do you know what I mean when I say functional? It's like a function of functions, right? And because we have integrals in there, in those statements, and we have a function of functions. And so, and we know that we can basically find the stationary value of that functional by computing the first variation of it, right? And so, doing that is, you know, what I mentioned last time is the Ritz method, right? So, by the end of the class, we're going to move from the, kind of classical Ritz method to the finite element method, which is just a piecewise implementation of that. And when we do that, we won't infer or use the quadratic functional. We'll just use the form above, the bilinear form. But let's go ahead and work one problem in this quadratic functional. And the reason for that is that if you see it by this finding a stationary value or minimizing that integral or the integral functional I, then you'll ultimately see that it works out to a problem that you're used to from calculus. Okay, so let's just work through the details. But first, let me just say about the Ritz method. Remember, the reason that the Ritz method is just one of those weighted integral methods, but the reason we like it is because it produces a symmetric coefficient matrix, and you do that by using the weak form, right? So we're going to use the weak form. This has the advantage that the approximating functions those are those phi's only need to satisfy the essential boundary conditions. Since the natural boundary conditions are included. So we seek u approximated by u of h equal to some set of unknown coefficients times some basis functions that are a function of x. We substitute this u of h into our integral. And integrate. And then we're left with, right? So the CJs are just constants, right? So whenever we substitute this approximating function into the integral, the constants can move themselves. You can move the constants outside the integral. Then you can integrate, and now you just have a function, right? Now you just have a function of x, Okay? And now if you want to minimize a function, what do? Take the derivative with respect to the unknown coefficients and you set them equal to 0. Right? That's just a problem from calculus, right? So we take the integral with respect to the unknown CJs, or take the partial derivative of I with respect to the unknown CJs, set them equal to 0, and solve the system of equations. So let's work an example. Here's our model equation. So we're going to solve this on the domain x equals 0 to 1 with two essential boundary conditions, that u of 0 is equal to 0 and u of 1 is equal to 0. So we won't work through the steps of the weak form, but let's reiterate what they are. There's 3 steps to develop the weak form. What's the first one? Multiply by a test function. Integrate. Step 2 is integrate over the body and integrate by parts to shift some of the differentiation onto the test function. And then the third step is to impose the boundary conditions, right? Now in this case, there's no natural boundary conditions. There's only essential boundary conditions, so there won't be any boundary condition terms in the integral. So if we do that, what we would get is the integral from 0 to 1 d dx del u and I separated the integral like that just to identify that this is the bilinear part and this is the part that only contains del u. And so from that we have our functional So that's our functional I. And, oh gosh. And so what we're going to do is we're going to assume that u is approximated by u of h, which is equal to, now here's where I'm going to put in my coefficients, c1 plus x, 1 minus x, plus c2, x squared, 1 plus 1 minus x, plus c3, x cubed, 1 minus x. So we'll plug that in, and then we'll have to basically just compute the integral I, and then take the derivative with respect to c1 and set it equal to 0. Take the derivative with respect to c2 and set it equal to 0. Take the derivative with respect to c3 and set it equal to 0. And remember, the approximating functions, or the fees, are these guys, and the rule on those is that they must satisfy the essential boundary conditions, and they must, the equation must satisfy the essential boundary conditions, and these approximating functions must be linear independent, right? Which clearly they are, because I have x and x squared and x cubed, right? So there's nothing I can add to this term to get one of these other ones, right? But what I couldn't use, for example, I could not use like x 1 minus x, and then here say use 2x 1 minus x, because I could simply just add. If I have x 1 minus x, and then I just add x 1 minus x, then I have 2x 1 minus x. So in that case, it would not be linear independent. Okay, so I don't want to work through the algebra, and so I'm going to use Mathematica to do this. So what I'm going to do is I'm going to say that u of x is equal to C1 x1 minus x. Can you guys see that okay? Let me see if I blow it up a little bit. Plus C2 x. Oh gosh, what just happened? Oh. Squared 1 minus x plus C3 x cubed 1 minus x. Okay. And so then I need to make sure that it satisfies the boundary conditions. I had one boundary condition that u of 0 equal to 0. That's already satisfied, right? So, sorry. Let's just say u of 0 is equal to 0, right? To verify that. And then u of 1 is also equal to 0. Right? So if you don't know what I did there, basically the first line I defined a function, right? And then I just evaluate the function at 0 in the second line, and then it basically plugs in 0 for x everywhere, and you can see that it is 0, right? And then also u at 1 is also 0. So satisfies the boundary conditions.
Shouldn't it be like C1 if you're plugging in 0, like the first term, C1 into 1 minus x?
No, it's x times 1 minus x. So if you plug in 0,
sorry. I thought it was it.
yeah, it's x times 1 minus. And that's clearly why I designed those. And again, we're gonna, by the end of class today, we'll talk about a more systematic way of designing the basis functions. But you can clearly see that's why I chose the basis functions to be x times 1 minus x, because the 1 minus x zeroes them out at 1. And then, of course, you have the leading x term. If you plug in 0 for it, it's going to be 0. Right? Okay, so I have an approximation of u that satisfies the essential boundary conditions.
The last term should be C3.
Oh, it should be C3, sorry. But it still won't change. Yeah, that was just a typo. Thank you for correcting me. But it doesn't change this, right? Okay, so now I'm going to evaluate the integral, right? So I have I equal to, and one of the reasons I like to use Mathematica in doing these kind of things in class is because Mathematica has syntax that looks just like the math, right? And so you don't have to know Mathematica syntax, and you can follow what I'm doing in code, right? So I'm going to create the integral here. Integral is going to go from 0 to 1. And so we had the derivative of u, actually, I can write it like this too. I can say u double prime of x squared, right? That's the first term, minus u of x squared plus 2x squared times u of x, and then I can integrate that over x, right? So there, it computed the integral for me, right?
Double prime and single derivative.
Double prime means the second derivative. Oh, it is the first derivative, sorry. Is that right? Yeah. Quadratic functional, yeah. So sorry about that. Yeah. So single prime is first derivative. Okay, so it integrates everything. This is the result of that integral. Now, I just have a simple function in the unknown coefficients, right? So I can basically write down 3 equations. So I'll take the derivative of II with respect to C1. That actually needs to be equal to 0. Right? So there's one equation. The derivative of II with respect to C2. There's the second equation. And the derivative of II with respect to C3. That's the third equation. All right, so I have 3 linear equations, and I can solve them. So solve equation 1, equation 2, equation 3 for C1, C2, C3. Oh, missed my equal to 0 here. There we go. And that is the answer. Right? So then what I could do is say u of x evaluated with that, and that is the final answer, right? So this, then, for example, I could plot on the domain x equals 0 to 1. That is the solution, right? Plotting the solution.
II is just basically I of u, right?
Yeah, I had to use I because in mathematics, I is the imaginary number symbol, right? So I can't assign anything to it. So that is approximate solution to the PDE, right? We'll see how things go from here, right? We'll see how let's work one more problem, and then we'll talk about, okay, that's an approximate solution, but how good is it, and how do we make it better? Okay. So let's talk more about interpolating functions.